All right, my friends, section 9.7 is about graphing in the polar coordinate system. All right, you're gonna hear my son and my friend in the background here. Anyway, so we're just gonna, the plan here is to figure out how in a pinch could you just t-table things out, which is probably the most powerful thing I could demonstrate. And then because t-tabling gets to be pretty tedious with some of these, the next step would be to learn the forms of the different differential equations, or sorry, not differential, excuse me, wrong class, the different polar equations, and then just kind of know going in what to expect, and then sometimes to do some analysis or a very minimal t-table approach, okay? But kind of day one, there's quite a bit of t-tabling things out. So, okay, so for example one, part A, let's say I ask you to graph r equals 2 cosine theta. If you're going to graph this, then, probably, day one, it would make sense to just kind of t-table things out. And I'm gonna use this type of polar graph paper here. And what really is probably going to get us the farthest is just doing any unit circle friendly type angle measure. So like 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and then we can stop at pi, and we'll kind of stop and take a break at pi, okay? So if you're plugging, let's say 0 in, you take the cosine of 0, because you're substituting 0 in for theta. Cosine of 0 is 1, you multiply it by 2, you get 2. Putting pi over 6 in, cosine of pi over 6 is root 3 over 2, and then you're multiplying it by 2, so you get root 3. Cosine of pi over 4, root 2 over 2, multiply it by 2, you get root 2. Cosine of pi over 3 is 1/2, multiply it by 2, you get 1. Cosine of pi over 2 is 0, multiply it by 2, you have 0. Cosine of 2 pi over 3 is negative 1/2, multiply it by 2, you have negative 1. Cosine of 3 pi over 4 is root 2 over 2, multiply it by 2, you have root 2. Cosine of 5 pi over 6 is negative root 3 over 2, multiply it by 2, you have negative root 3. And cosine of pi is negative 1, multiply it by 2, you have negative 2, okay? So just some comments really quick before we go on. Root 3 is approximately, do you remember? 1.7, and root 2 is approximately, there we go, 1.4, okay? So if you are t-tabling this out and then plotting the points, of interest, then, you'd plot the point, that corresponds to theta being 0 and r equaling 2. And then theta being pi over 6, and then your r value being about 1.7. Pi over 4, 1.4. Pi over 3, 1. Pi over 2, 0. 2 pi over 3. Okay, so this is fun with the negative r values. You're facing 2 pi over 3, but you're going to go away from it 1 unit. So you're going to go toward 5 pi over 3, 1 unit. 3 pi over 4 root 2, negative root 2. So you're facing 3 pi over 4. You're going to go away from it about 1.4. So that means you're going towards 7 pi over 4 that far. 5 pi over 6, negative about 1.7, so you're going toward 11 pi over 6, about 1.7. and then at pi you're going -2. Now, there are many points that would have occurred in the angles, the infinitely many angles that happen between 0 and pi/6. And so what we're just doing is getting enough points of interest so you could imagine those infinitely many points that we would have gotten likely would have followed this pattern. And hopefully you can see that the graph that would result is a perfect circle. Now, a very good question would be, well, hey, you stopped at pi. What about, what about the rest of the unit circle? What would have happened? And so, such a good question. So I'll just kind of continue this very tall t-table here. So if you were to continue, like, let's say 7 pi/6, so cosine of 7 pi/6 is -√3/2. Multiply it by 2, you have -√3. And so what you can see here is at 7 pi/6, you got -√3. So it would be back on top of the first one. If we were to go to 5 pi/4, we'd end up with -√2. When you evaluate it into the rule, so it would be right back on top of pi/4, and right on top of the point that we had before. And so something that comes in really handy when you get to a calculus class is to actually understand that if you go all the way around the unit circle, that this graph actually draws itself twice. So the red would be what it would have drawn between 0 and pi, and then the green is what it would have drawn here. I guess it's kind of hard to see that that's green on top of red, but anyway, but the green would be the second, going from pi to 2 pi, it would have drawn itself again. So right now, really the point as a pre-calculus student is, can you graph this at all? And I'm sure you'll be able to, but as a calculus student, it's particularly useful to be able to know that it draws itself twice when you go around the unit circle one full time. So, so for part B, let's play with what happens if I asked you to convert the equation r equals 2 cosine theta, the one we just graphed, into rectangular form. And this is, kind of some review of something that we did in the last section, but let's just play with this. Let's see, what happens when you do that. So, so I'm going to copy r equals 2 cosine theta, and let's think about what could you swap in for cosine theta, for example. You could replace it with x over r. And then you could multiply both sides of this equation by r, and you'd end up with r squared equals 2x. And then what could you replace r squared with? You could replace it with x squared plus y squared. Now, some folks can look at this and be like, oh yeah, that's a circle, boobity-boo. But let's actually take this a little bit farther. We're actually done at this point with the directions, but let's just have some fun with this. Let's ride this sucker out. Let's say you wanted to graph this conic section that you have here. You can tell that it's some form of an ellipse because the x term is squared and the y term is squared, and they're both positive. So this should end up being some form of an ellipse. So let's subtract the 2x over. I'm going to go ahead and show like some grouping here, and then you'd have y squared by himself and then equals 0. Let's complete this square in the group for the x terms here. Divide your linear coefficient by 2 and square the result. You'll end up with 1. I actually did just add 1, so I'm going to add 1 to the other side. So what's this equation now say? It says, let's factor this. This would be x minus 1 quantity squared plus y squared equals 1. And if you want, you could always put this over 1 squared and this over 1 squared to really show off that this sucker is an ellipse. And it's not just any ellipse, it's a perfect circle. And where's it centered? Well, it got shifted to the right one and it didn't get shifted vertically at all. So its center would be here at 1, 0. And then you would go from in the x direction, you'd go right and left 1 unit, and then from the center. And then in the y direction, you'd go up and down 1 unit. And then you could graph your ellipse, but it's a perfect circle because these two values were the same. So that's kind of fun. So what that does, if you kind of know going in what the equation, what type of polar equations turn into circles, then it means that you wouldn't have to do all this t-table work. You could just do maybe a couple, maybe just do, 0, pi over 2, and pi or something, and be done. Just kind of have enough points of accuracy to know where your circle goes. So there you go. Okay. Moving on to example 2. Remember, my friends, that with examples, you're probably best off before you watch my explanation. You're probably best off just pausing the video and trying things on your own. So example 2, let's do graph. Y equals 4 times sine of theta. So you could t-table this out, which I'll probably go ahead and demonstrate. And typically when we t-table things out, unless kind of told otherwise, we just kind of do unit circle friendly stuff. And then I'll grab a piece of polar graph paper here. So if we were evaluating, oops, that is not the pi symbol. Okay, funny. Okay, so if we were evaluating everything here, we, sine of 0 is 0 times 4, still 0. Sine of pi over 6 is 1/2 times 4 is 2. Sine of pi over 4, root 2 over 2 times 4, you get 2 root 2. Sine of pi over 3 is root 3 over 2 times 4, you get 2 root 3. Sine of pi over 2 is 1 times 4 is 4. Sine of 2 pi over 3 is root 3 over 2 times 4, you get 2 root 3. Sine of 3 pi over 4 is root 2 over 2 times 4 is 2 root 2. Sine of 5 pi over 6 is 1/2 times 4 is 2. And sine of pi is 0 times 4 is 0. So, and notice I just went from 0 to pi. These graphs tend to draw themselves twice if you go around the unit circle twice. Okay, or sorry, if you go around the unit circle once, it draws itself twice. Okay, so plotting these points, we'd have 0, 0, which is just the pole, pi over 6, 2, pi over 4, 2 root 2. Now let's think about this. Root 2 is 1.4 times 2, so that's about 2.8. So pi over 4, almost 3. Let's see, pi over 3, so root 3 is about 1.7. Multiply that by 2, what is that, about 3.4? Okay, so pi over 3, about 3.4. Pi over 2, 4. 2 pi over 3, and then remember this is about 2, oops, sorry, about 3.4. And this was about 2.8, so 3 pi over 4, about 2.8. 5 pi over 6, 2. And then pi gets pulled back into 0. if you were to plot the infinitely many points that would have resulted from the infinitely many angle measures, you know, that occur in between, you would end up again with a perfect circle. So we'll go ahead and fill this in. Okay, and it's probably going to look like a mess, so please just pretend that it looks like a perfect circle. Okay, something like that. Okay. And if you are doubting at this time in any way that if you were to continue around, you know, plugging in 7 pi over 6, 5 pi over 4, 4 pi over 3, then by all means continue your t-table out and then just kind of see what happens. What you'll find out is you start getting negative r values and it kind of starts graphing on top of itself again. Okay? So a summary for what we've done so far. Is that circles have polar equations of what form? So if you look at the last two examples that we did, so this was example 1, and this was the graph of r equals 2 cosine theta. And if you look at the example that we just did here, r was equal to 4 sine theta. Then what would kind of just a general form be for something that turns out to be a circle? So the form would be r is equal to some value, I'll use a to mean an arbitrary constant, times cosine theta, or you could have r equals a times sine theta. Boop, 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 like so. And then what is the significance of that a value? Here you had r equals 2 cosine theta, and the farthest away from the pole you got was 2. And then here you had r equals 4 sine theta, and the farthest away from the pole that you got was 4. And so a claim would be that this value is your diameter of your circle. Now, you could have a negative number here as well. All that would do is kind of reflect the graph over to the other side for the most part. So because a could be a negative number, we would just basically say where the absolute value of a is the diameter of the circle. And now there's more that that you could know or kind of write down as far as a summary for circles, but I really like kind of being a minimalist, and so really what I would do is memorize just the forms that turn out to be circles, and then we'll do an example just to kind of show you how minimalist you could kind of be with that, okay? So example 3. Let's say I ask you, you know, from here on out, if I was to ask you to graph something like -2 times sine of theta. So the trick is to know, just because of the form, that you're expecting a circle, and it's also kind of nice to know that the diameter would be the absolute value of -2, so you're expecting a diameter of 2. But if I was to, you know, do this problem, I would, and either in my head or on paper, likely in my head because this is going to be a very simple thing to do, I would likely plug in just simply 0 and pi over 2, and possibly that's it. Because if I know I'm expecting a circle, If by the time I plug in 0 and pi over 2, I might actually have a pretty good idea as to where this is going. So let's plug 0 in. Sine of 0 is 0 times negative 2 is still 0. So boom. Let's plug pi over 2 in. Sine of pi over 2 is 1, and then times negative 2 is negative 2. So you're facing pi over 2, you go negative 2. Well, we were expecting a circle, and we were expecting the diameter to be 2. And so what that would mean is this is probably the center right there. And then if I was to graph it, I would just go up 1, down 1. Because if the diameter is 2, the radius is 1. And then I'd go to the right one. And how do I know where 1 is? Well, you know, I could just line it up with this little ring right there into the left one. And then you could fill it in with your best shot at a perfect circle. So there you go. All right, my friends, so that's all I have to say about circles. So let's move on to another family of equations, and we're not going to spend a lot of time on this because honestly, a lot of being good at polar graphs is just being willing to t-table it out. So example 4. You know, memorizing what form causes what shape, and then being willing to t-table it out. So let's say I ask you to graph r equals theta, and then let's say I want this to happen for theta greater than or equal to 0. So just, you know, let's just worry about positive values for theta. And so I'll get some polar graph paper here, but really I would encourage you to do that, you know, plug theta in and get r out and just see what happens. And I'll give you a minute to do that when I cut out a piece of polar graph paper for myself. Okay, and that was not a lot of time at all. Again, if you haven't had enough time to think about it, I'd say pause the video and think about it for yourself there. So, you know, I would seriously just, you know, get going with all the unit circle friendly stuff, you know. And then I'm going to probably show on paper what I'm thinking up to pi over 2, and then I'll probably just verbally say the rest here. So if I plug 0 in for theta, r would be theta. So that would result in this point here, 0, 0. If you put pi over 6 in for theta, you get pi over 6 out. This is a very simple equation. Pi over 6, remember pi is about 3.14 over 6. So I'm going to say roughly, I'm going to rudely treat pi like a 3. So this is, let's say a little bigger than 1/2. So I'll just say 1/2 and a little bigger there, okay? So we're going to face pi over 6, and we're going to go toward it, you know, a little bigger than 1/2. Pi over 4, put pi over 4 in, you get pi over 4 out. Pi is roughly 3, it's a little bigger, so you'd have something about 3/4 and probably a little bigger than 3/4. So face pi over 4 and go a little bigger, I guess, than 3/4. Pi over 3, put pi over 3 in, you get pi over 3 out, which is roughly 1. Of course, a little bigger than 1. So you're facing pi over 3, you're a little bigger than 1. Pi over 2, put pi over 2 in, you get pi over 2 out, since r is just theta. And then, so this would be roughly 3/2, you know, something a little bigger though than 3/2. So you're facing pi over 2, and you're going to go something a smidge bigger than 1.5, okay? Okay, I'll add a couple more here. So 2 pi over 3, you get 2 pi over 3 out. Okay, I'm going to very rudely treat pi like a 3 and cancel the 3's. So you'd have something roughly 2, but it would be a little bigger than 2 since pi is a little bigger than 3. So 2 pi over 3, and then you're going to go out just a little bigger than 2, Okay? Now, if I continue in this manner, I'm just going to start saying it verbally instead of doing it on the T-table. You know, you put 5 pi over 6 in, you're going to get 5 pi over 6 out. So that would be like, kind of like 5 times about a half, you know, so something a little bigger than 2.5. Pi is 3.14, so that's what you'd get out. And then I'm probably gonna, I don't know, let's kind of skip a couple. Well, actually, nah, I won't be cheapo. How about this? Pi over 6, that's like a half, so 7 times a half is 3.5, but it would be a little bigger. 1, 2, 3.5, a little bigger. Okay. 5 pi over 4 would be like 5 times 3, so 15 over 4. What is that? 12 and 3/4. So let's say almost. Wait, what did I just say? That was crazy. 3 and 3/4, because we'd have 15. 3 and 3/4. Okay, so almost 4. 1, 2, 3. Arithmetic hard. Okay, let's let the pi and the 3 kind of cancel. So you had something a little bigger than 4 here. 3 pi over 2 would be like 9. Would be like 9 over 2. So 4.5. 1, 2, 3, 4.5. A little bigger, you know. Okay. 5 pi over 3. The pi and the 3 could cancel. You have something a little bigger than 5. 7 pi over 4. What is it? About 21 over 4. 5 1/3 ish, bigger. 11 pi over 6 is like 11 times a half, so 5.5, but a little bigger probably. And then 2 pi, when you come back to 2 pi, you've got about 6.28, so that would be like off my paper here. Boop, about here. Okay? So if you connect these dots, of course there are angles that are not unit circle friendly that we could have grunged out if we really wanted. But if you connect the dots, I hope it makes sense. You could have gone around the unit circle infinitely many times, so this thing could have grown and grown and grown. You know, what kind of graph do you get with an equation that's just so simple, like r equals theta? I think a lot of people would say you get a spiral. So there you go. If I had something like r equals 1/2 theta or r equals 2 theta, think about how different would that have been. And even you could even T-table it out if you wanted, but it would be very similar. It's just your theta values here would have been half of what they would have been here, so it would have been coiled tighter because you're not going out as far for your r value. And then here r equals 2 theta, your r value would be double your angle, so you'd still get a spiral, but it would be coiled kind of looser. So I hope that makes sense. So really that's all I have to say about spirals. So your summary is in the polar coordinate system, spirals have the form, or have, let me word that a little differently, sorry, have equations of the form. R equals some constant, some arbitrary constant, times theta. There you go. All right, my friends, I think this is a fine place to stop for part 1. I hope this is making sense. I believe you should be able to do your part 1 homework now. And feel free to email me or private message me if there are problems in your problem set that don't make sense. Take care, everybody.